Welcome back to Quantify Your Career. And as I had mentioned last time, I gave an introduction to the hands on project which we are going to work on, which is building a volatility surface model. And that's what we are going to do today. So, we are going to build something that sounds intimidating at first, but once you see it, you will realize it's actually a pretty straightforward idea. So, we are building an options volatility surface. Think about it like this. You know how a weather app shows you a map with different temperatures in different places. A volatility surface is basically the same thing, but for options. Instead of showing temperature, it shows volatility. And instead of different cities or regions, it shows different strike prices and different times until the option expires. So the volatility surface answers one simple question. What volatility is the market implying right here at this specific strike price and at this specific maturity? And we are going to build that entire map from scratch in Python step by step so you can actually see it, rotate it in 3 dimensions, and understand exactly what's happening under the hood. So we are going to implement the Black-Scholes formula ourselves. We are going to compute implied volatility using a numeric root finder. We are going to organize everything into a grid, smooth it into a continuous surface, and then plot it in 3 dimensions. First, let me start with this fundamental question. Why do we even need a surface at all? So, in the textbook Black-Scholes world, volatility is just one constant number. You might say, okay, volatility is 20%, and you use the same 20% for every option on the same underlying, no matter what the strike price is or no matter how far out the expiration is. But that's not what happens in real markets. And this is one of the key points that John C. Hull emphasizes when he discusses volatility and implied volatility in his work and in the book. Markets don't behave as if volatility is a single constant that works for every strike and every maturity. Instead, when you back out implied volatility from actual market prices, you discover something interesting. That implied volatility changes. It changes across strikes. When you plot implied volatility against strike price at a fixed maturity, you often see what's called a volatility smile or a volatility skew. The implied volatility might be higher for out of the money puts, lower at the money, and different again for out of the money calls. It also changes across time to maturity. When you look at options with the same strike but different expiration dates, their implied volatilities can be quite different. And that's called the volatility term structure. When you put both of these patterns together, strikes on one axis and maturities on another axis, you get a volatility surface. So the volatility surface exists because the market itself is telling you that volatility is different in different places. The surface is literally the market's way of pricing uncertainty differently depending on where you look. Now, let's talk about what implied volatility really is. In the most straightforward terms possible, you never directly observe volatility in the market. What you observe is the actual price of an option. Someone is willing to pay you $3 for this call or $5 for that put. That's what you can see. So here's what we do. We take pricing models like Black-Scholes and we turn the problem around. So normally Black-Scholes works like this. You input the volatility and it outputs an option price. You input even other parameters along with the volatility. Now, with implied volatility, we go backwards. We ask what volatility would make the Black-Scholes formula produce this exact market price that we are observing. Now, that volatility, the one that makes the model match the market, is the implied volatility. And John Hull describes implied volatility as the vol that, when plugged into the pricing model, gives you the observed market price. Here's something really important to understand. Implied vol is not a forecast of future volatility. It's not a prediction. It's more like a translation. You're translating market price into volatility language. And the reason traders and quants prefer to work with implied vol rather than raw option prices is because it gives you a common language. Option prices are really hard to compare across different strikes and maturities, but implied volatilities you can compare much more easily. And you can immediately see which options are expensive in vol terms and which are cheap. So let's lay out the entire flow of what we are building in this notebook. So first we start with a table of option prices organized by strikes and maturities. Each cell in this table represents the market price of a call option at that particular strike and that particular time to expiration. Then we implement the Black-Scholes call pricing formula from scratch. We need this because it's the forward direction. You give it some vol and it gives you an option price. We need to be able to do this reliably because we are going to use it a lot of times later. Then is the heart of the whole project. So for each market price in our table, we will solve backwards for the implied volatility. And we are going to use a numeric root finder to figure out what volatility makes our Black-Scholes function produce the exact market price. Then we put all those implied volatilities into a grid with the same structure as our price table. So strike prices on one axis, maturity on the other, and each cell contains implied volatility for that strike and maturity combination. And then we smooth that grid because markets give us discrete points, but we want a continuous surface that we can query anywhere. So we need interpolation. Then we visualize everything. We create an interactive 3D plot where you can rotate the surface and see its shape. We also create the two key slices that practitioners actually use. The smile shows you how volatility changes across strikes at a fixed maturity, and the term structure shows you how volatility changes across maturities at a fixed strike price. And finally, we validate everything by repricing. We take the implied volatilities we computed, plug them into Black-Scholes, and then check what we get back, if we get back the original market prices. And that's sort of a proof that our solver worked correctly. Okay, so the first thing to do in the notebook is to write the Black-Scholes call pricing formula ourselves. And you might wonder why not just use a library? Because later, when we are finding implied volatility, we are going to call this function hundreds or even thousands of times. We need to understand exactly what it is doing and we need it to be stable. So we implement a function where you give it a spot price, strike price, time to expiration, risk-free interest rate, and the volatility. And it gives you back the call price. Now, conceptually, here's what's happening in Black-Scholes. The formula is taking uncertainty about the future and turning it into probabilities. And then it is discounting cash flows based on those probabilities. So if you're trying to explain this to a kid, you might say the option is like maybe coupon. It might become valuable in the future or it might not. And Black-Scholes is saying how likely it is that it ends up valuable and what is the worth right now. And that's why the formula has those cumulative normal distribution terms in it. They represent probabilities under the model's assumptions. The model assumes that the log of the stock price follows a normal distribution, and those probability terms tell you how likely it is that the option expires in the money. Now in the code, we compute that what are called D1 and D2, which are intermediate values that show up in the formula. Then we evaluate the cumulative normal distribution at those points, and then we combine everything to get the call price. We also add some basic safeguards, like if the time to maturity is 0, we just return the intrinsic value, which is the maximum of 0 and spot minus strike. And we make sure volatility is positive so we don't accidentally divide by 0. These safeguards are important because the implied vol solver is going to call this function over and over, and if this function is not stable, the whole pipeline will break. So this is the forward direction. Volatility goes in, option price comes out. We need this working perfectly before we go backwards. Now for this teaching notebook, we are going to do something different. Rather than downloading real prices, we are going to generate synthetic market prices. Since we are not using the real prices, we can optionally add a little bit of noise to mimic real world bid-ask spreads or quote messiness. But by default, we keep this noise off so the surface looks clean and you can see the methodology clearly. The point is we know the true volatility surface because we created it. And then we can test whether our implied volatility solver recovers it correctly. Let's get to the main part, the real core of this project. We need to find implied volatility. And here's the key insight. For each option in our table, we have a market price. Let's call it C market. And we want to find the volatility such that when we plug it into Black-Scholes, the price that comes out matches C market exactly. In other words, we want Black-Scholes price with sigma to equal C market. So we can define an error, the model price minus the market price, and we want that error to be zero. And that's literally the definition of a root finding problem. We're looking for the root, the value of sigma that makes the error function equal to zero. Now, there are several numerical methods which can be used here. Newton's method is popular because it converges quickly and it uses something called vega, which is the derivative of the option with respect to volatility. But Newton's method can be tricky if you're learning because if you start with a bad initial guess, it can fail to converge to a nonsensical value. So for this notebook, we're using something simpler and more bulletproof, which is bisection. How bisection works is you start with a very low volatility, maybe 1%, then you price the option at that volatility and you get a low price. Then you pick a very high volatility, maybe 200%, you price the option at that volatility and then you get a very high price. The correct volatility is somewhere between those two values. And then you keep cutting that interval in half and you try the midpoint. If the price at that midpoint is too high, you know the correct volatility is in the lower half of the interval. If the price at the midpoint is too low, the correct volatility is the upper half, in the upper half. And then you repeat the process, halving the interval each time until you've narrowed it down to you've narrowed it down so much that your model price matches the market price to within some tiny tolerance. Bisection is slower than Newton's method, but it is extremely stable as long as the option price increases with volatility, which it does for standard call options. So for this, bisection is perfect. Our implied volatility solver starts with a low vol bound and a high vol bound, checks that the root is actually bracketed between these bounds, expands the bounds if needed, and then repeatedly halves the interval until the pricing error is smaller than some threshold, maybe 10th of a cent. So this is just a root finder. Now we do something very simple but powerful. We loop every call in our price table. Now for each strike, for each maturity, we take the market price in that cell and we call our implied vol solver to find that sigma that matches the price. And then we store that implied volatility in a table. Same shape as the price table and same strike prices, same maturities. But now instead of those option prices, each cell now contains implied volatility. So this is important to pause and recognize. This is the volatility surface, which is just a table. It's a grid of numbers. The three-dimensional plot we are going to make later is simply a visual representation of this table. So the surface is already here in this grid. Okay, so now we have a grid of implied volatilities. But here's the problem. Markets will give you discrete points. Maybe you have strike prices every $5, 95, 100, 105, 110, and maybe you have maturities at 1 month, 3 months, 6 months, and 1 year. But what if you need to price an option with a strike of 102 or a maturity of 2.5 months? So those aren't on your grid, and you need a way to fill in those gaps. So that's where interpolation comes in. You need a smooth function that takes your discrete grid points and creates a continuous surface. Now, there are many ways to interpolate, and some of them will create some weird bumps or strange behavior if you're not careful. But because our data sits on a nice rectangular grid, we can use something called a bicubic spline interpolation on that grid. And this tends to produce a smooth, well-behaved surface. In the notebook, we interpolate over moneyness, which is strike divided by spot to normalize the strike prices, and over maturity. So we evaluate the interpolated function on a dense grid so that we can plot it smoothly. And we clip the resulting values to avoid any weird negative overshoots that can sometimes happen with splines. So now we plot the surface in 3 dimensions using Plotly, and this is where things get visual. You'll see strike price along one axis, time to maturity along another axis, and implied volatility on the vertical axis. And because we are using Plotly, you can click and drag to rotate the surface, zoom in and out, and really explore its shape. We also plot the original grid points as dots on the surface so you can visually check that the smooth surface is behaving sensibly around the actual data points. If the smooth surface deviates wildly from the points, that tells you something went wrong with the interpolation. When you look at the table of numbers, you don't really see the shape, but when you see the surface, you can immediately tell if it's a skew, if the term structure is upward sloping or downward sloping, if there are any weird features you need to investigate. Now we can create two plots that matter enormously in practice. The first one is the smile plot, or sometimes the skew plot. Usually, smile is seen with FX options, and skew is usually seen with equity options. Now, here's what that shows. You pick a fixed maturity, for example, 3 months, then you plot implied volatility on the vertical axis and strike price on the horizontal axis using only options that expire in 3 months. If you do this for several different maturities, you get multiple curves, one for each maturity. And this directly connects to what even Hull had mentioned in his book about volatility smiles. When you compute implied volatilities from actual market prices, they depend on the strike price, and often you see a U shape like smile, or sometimes an asymmetric skew. And even if you don't understand like the calculus behind any of this, the plot tells you something very fundamental. Volatility is not constant across strike prices, and the market is pricing options at different strike prices as if they have different volatilities. And that's important because it tells you the market is concerned about tail risk, about big moves in ways that the simple constant volatility Black-Scholes model doesn't capture. The second key plot is the term structure. This is another slice through the surface, but cutting it in a different direction. You pick a fixed strike price, usually something near at the money, so it's actively traded. Then you plot implied volatility on the vertical axis and time to maturity on the horizontal axis. This shows you how implied vol changes from short dated options out to long dated options. So this means implied vol depends on maturity too, not just the strike prices. Sometimes, sometimes short volatility is high and long term volatility is low, which gives you a downward sloping term structure. Sometimes it might be the opposite, and at times it might even be humped high in middle maturities. And the term structure tells you about the market's expectations over different time horizons. So if short term vol is much higher than long term, that means the market is worried about something happening soon, but expects things to calm down eventually. And we typically plot a few strike prices near the spot price to see how the term structure behaves in the most liquid part of the market. These two plots, the smile and the term structure, these are what most quants look at on a daily basis. They summarize the most important features of the surface without needing to rotate the 3D object. Next, we validate our results. And how we do it is by repricing. So we take each implied volatility that we computed and then plug it back into Black-Scholes formula. And then we compute the model price. Then we compare the model price to the market price we started with. So if our solver worked correctly, those two prices should match to within a tiny fraction of a cent. So this is just your correctness or sanity check. And then if that fails, you will see big differences between repriced values and the market prices. Then something went wrong. Maybe the solver did not converge properly. Maybe there was a bug in Black-Scholes implementation or a data problem. And you always want to do this sanity check in real workflow and in projects because without it, you might be building a beautiful looking surface that is actually giving you completely wrong implied vols. And then all your downstream pricing and risk management might go wrong too. So in the notebook, we compute the maximum repricing error across the entire grid. And if the error is less than, say, tenth of a cent, we are good. And the solver has worked. Now, let me take a step back and talk about why people care about building this surface in the real world. So if you're pricing just one option, you can probably get away with looking up one implied volatility code and using that. But as soon as you have a portfolio with multiple options across different strike prices and different maturities, you need consistency. Otherwise, you price one option with one volatility number, you price another option with a different vol number, and you have no coherent picture of what's happening. You cannot compare them and hedge them consistently, and you don't really understand your risk. So the volatility surface gives you that coherent picture. It's like the market's way of saying, here's how volatility behaves everywhere. And once you have that surface, you can do real things. You can price options at strike prices and maturities that aren't exactly on your grid. And you have a continuous function now, so you can query it anywhere. You can compare different regions of the surface, and you can say short dated out of the money puts are pricing in 25% volatility, but long dated at the money calls are only pricing in 18% volatility. That tells me something about what the market is worried about. And then you can also run scenario analysis. You can ask, what happens to my portfolio if short term volatility spikes by 5%, but long term volatility stays the same? Now, because you have a surface, you can shock different parts of it independently. You can backtest option strategies that roll positions over time. So, if you're selling a 3 month option every month, you need to know how implied volatility behaves at that 3 month maturity over time. And the surface helps you understand that. So, the volatility surface is not just an academic exercise or a project, it's also a tool that lets you price consistently, manage risk coherently, and understand what the market is actually telling you about uncertainty. So let me just quickly recap everything we did in the notebook step by step. We started with option prices, organized them in a grid by strike and maturity. We implemented the Black-Scholes call pricing formula from scratch, so we understand how exactly it works. We inverted that formula using a bisection root finder to extract implied volatility from each market price. Then we created a complete implied volatility grid with the same structure as our price table. Then we smoothed that grid along spline interpolation to create a continuous surface we can query anywhere. Then we visualized the resulting volatility surface in 3 dimensions and plotted its two key slices, the smile or skew and the term structure. And we validated everything by repricing the options and checking that we recover the original market prices. So that's the full volatility surface pipeline. Now, this is implemented in Python, but I'll also be giving a brief overview of how we can do this in Excel. Until next time.